Okay, not too much new in this situation. We are going to look at curve sketching. You've seen this before. We're just going to get some more practice with it. So nice days, you already know how to do it. We're just going to make sure that it sets within your brain and you feel like you know what to do for the test. You're not going to be able to press the graph button on your test, okay? So when you get to your test, you got your calculator out, you can't press graph because I can't have you just sketching the graph on your calculator, copying it down. So fair enough?
Right.
Okay, good. So if you want to, so our goal is to sketch a perfect graph in this section. Okay, we're gonna do 2 problems today. We'll do one tomorrow, get you guys some time to work. But these are the things that we like to keep in mind if we are sketching a curve. The first one would be the domain and the range. In this case, it is a polynomial, and so the domain is all real numbers, and the range is all real numbers. Okay. If it was a rational function, meaning you have something in a denominator, then we can't have the denominator equal to 0. But we should be able to think critically about the domain and the range. Okay. Second thing we should be able to think about is the intercepts. And when you're looking for the intercepts, in order to find the x-intercept, we set y equal to 0. In order to find the y-intercept, we set x equal to 0. We've done that before. We've done a whole study on that. I don't really try to think about symmetry too much. It's not that big of a deal. But asymptotes. Asymptotes are important. Asymptotes occur a lot of times where the denominator is equal to 0. And asymptotes also happen when you consider the limit as x approaches positive or negative infinity of the function. So that's the piece of our lesson that we didn't quite get to on Friday. We're just going to skip that part. We'll introduce it today. So no big deal. You guys already know how to do it. Intervals of increasing and decreasing. Well, we know that you have to consider where f prime is greater than 0 and where f prime is less than 0. So we have to be able to navigate our derivative tests properly. Our local max, that occurs when f prime changes from what to what? Positive to negative, very good. And the local min happens where f prime changes from negative to positive. So we're looking for those change of signs for the first derivative. Now it'll tell us local max or local min. Concavity, where it's concave down, where f prime double prime is less than 0. And it's concave up where f double prime is greater than 0. That's our behavior for concavity. I forgot to write one piece in here, and that'll be inflection. My bad. I made a mistake, and for that I will award each of you $1. Well, no, I'm keeping track. You guys owe me $1 for every mistake you make, so we're, so you don't owe me as much as you used to, okay? Inflection happens where f double prime changes sign, positive to negative or negative to positive. And again, the end behavior of the graph, what happens as it heads out to positive and negative infinity? We use our awesome concept of limits in order to answer that question. And that will often determine for us asymptotes as well. So. We good? All right, let's navigate. Use the following guidelines to sketch a curve of this. This will be a large portion of your test, okay? We should be able to take any type of polynomial, especially that we see, and be able to identify these important pieces. What I like to start with is actually the end behavior of this function. It is a cubic. It's going to end going up, down, what? Up, why? It's positive, everybody agree? So the limit, the end behavior will be the limit as x goes to positive infinity of the function is equal to infinity. Okay, so it heads on up. How about where does it start? Does it start up or down? Down, why? It's odd, so the limit as x goes towards negative infinity of the function is equal to negative infinity. So that tells me it starts down, finishes up. Everybody locked in there? Okay. So as we consider the domain of this function is all real numbers because it is a polynomial. Nothing crazy about that. There's nowhere where it's undefined. And so since this is behavior, it does not have vertical asymptotes or horizontal asymptotes. We'll show you an example that's different on the next one, okay? So no vertical asymptotes, no horizontal asymptotes. That's the end behavior, okay? I'd like to now consider with you guys the x and y intercepts. In order to do that, I will again plug in 0 for x and 0 for y. Notice that if I plug in 0 for x, I get 0 for y. So that means it has a y-intercept of 0. Now I'll plug in 0 for y. So I have 0 is equal to x cubed minus 2x squared minus 3x. Okay? I'll factor out an x, and I get x squared minus 2x minus 3. Does that factor? It does. And I have 0 is equal to x times x minus 3 times x plus 1. And so I can see that it has 3 x-intercepts, 0, 3, and negative 1. All this we've seen before really in our college algebra class. Love the Christmas shirt today. Are we going to have a Christmas, kind of, maybe? Is that, can you stand up and show everybody? Is that a Christmas shirt?
No.
Kind
It
of.
wasn't meant to be.
It's got some green and red, and sometimes there's stars on Christmas trees.
It can be Christmas. Why
Okay.
not?
Okay. Are we going to have an ugly sweater
Still
day?
gonna wear it in the summer though.
Student council, are we having like something like Christmassy?
Dress up days.
Dress up days?
But we can't do like Christmas.
Okay.
So, like holidays.
Holidays?
Yeah.
Holiday sweater, not Christmas.
I might try to get that same one you got there. All right, so we know where it crosses the x-axis and the y-axis, but we don't know how high or how low it goes. So what I'm going to need to see from you on your test is I'm going to need to see you do a first derivative test. And I'm going to see you need to do a second derivative test. You must produce the derivatives and show me your work, how you generated the results. Because I know that some of you can think through this without necessarily even generating that work. What is the first derivative? So I'm trying to find out where that is equal to 0. I know that that makes the shape of a parabola, okay? And I'm trying to figure out where it crosses the x-axis. I'm going to use my handy-dandy calculator to figure this out, because on my calculator, I produced this wonderful thing called the quadratic formula. And instead of going through the whole process or pressing y equals or graph or anything like that, I can simply go into my program. For those of you who don't have it entered in, you're going to go visit Mr. Gentz's website on his YouTube channel, where he's created a 4-minute, 2-second video and shown you how to do this. I turn on my calculator, I clear it, I go into program, execute the quadratic formula, and I type in 3, -4, and -3. And I get 1.86 and -0.53. Okay, that's my method. I like to use the graph. I notice that it is positive here and positive here, and it is negative there. I will consider that first derivative, and I will make use of that in order to determine what. What can you tell me now? Increasing where? From? negative infinity to, yep, and then from 1.86 to infinity. Wherever the first derivative is positive, that's where it is increasing. It is decreasing where it is negative, which would be from negative 0.53 to 1.86. What else do I know? Yeah, it has a local min and a local max. The local max happens where it changes from positive to negative, which would be at what? Negative 0.53. And the local min happens where it changes from negative to positive, which occurs at 1.86. We will wait to get our y values here in a little bit. Everybody good with that? Okay, in order to get concavity and flexion, I need to find the second derivative. So I'm going to go ahead and produce the second derivative. And the second derivative would be 6x minus 4. We're going to use the Mika method here. Yep, I just said that. If we solve it equal to 0, we get 2/3. And we're simply just going to do a number line check. Mika, give me a number that is less than 2/3.
-2.
Awesome. I love it when you use the number 0. So we're going to plug in 0, and we get 0 minus 4 is negative. Negative 2 would work as well. Give me a number that's bigger than 2/3, Mr. Jacob. 5. 6 times 5 is 30 minus 4. Great, that's positive, okay? So I use my number line test. You can use a graph or a number line test. Either one is just fine. And that tells us our important characteristics of both concavity as well as inflection. Concave up from negative infinity to 2/3. Concave down from 2/3 to infinity. The inflection happens at the coordinate of 2/3. We good? What do we need to do now before we generate our graph? Yeah, put in our table. Let's come up with these y values here. So I'm going to plug in, again, I don't mind, oh, just broke the law, press graph. Going to y equals, we press 3, no, I'm sorry, x to the third, minus 2x squared, and then minus 3x. And I go into my table, and I'm going to type in these important values. I believe we had a negative 0.53. I believe we had a 2/3 or 0.6 repeating. And I believe we also had a 1.86. And those are producing then y values for me that I can make use of. I've got 0.88, 0.88. I have negative 2.6. Whoop. Negative 2.6. And then I also have negative 6.06. Ty, I would like it if you would judge me today. Okay, scale 1 to 10. I'm going to try to draw a perfect graph. Got it? As I look at my scale, it goes down to 6. On my x-axis, I'm only needing to go over 3. So I'm going to do 2, 4, 6, 8. And I'm going to do 1, 2, 3, 4. I'm going to start by plotting my intercepts of 0, 3, and negative 1. I'm going to plot my minimum and my maximums. My minimum is 1.86. So right about here, and then down 6. My maximum is at negative 1/2, and just about +1. And then my inflection at 2/3 and -2.6. We're gonna go right about there. And remember, we know it starts down and it finishes up. So I'm gonna let's see if I produce the perfect graph. I go into my calculator. I'm going to change my window so that I am at a -4 and a +4. And I'm at a -8 and a +8. Tick mark every 2. And I press graph. Okay, Ty, what do you think? Scale 1 to 10. 5. Oh shoot! I was thinking more like a 7.5. What do you think I need to do to improve? Because I want to get better, Ty.
Maybe a little less steep.
Okay, so I'm a little bit too,
Yeah.
like this is a little bit wider, and I'm not really that wide, am I? Okay, all right. I know I can do better. I'll continue to try. Rosa, what would you have given me? Do you think he's being harsh with that grade of 5?
I do feel like that because I mean, you hit all the points, so I'd probably give you more like a 7 or an 8, you know?
All right. If I ever need to take this class again, I'll take it. I'll have you be the teacher. That way I'll get a better grade.
I don't think that would go real well.
This is what we're looking for, and that is an excellent graph. It only rates a 5, but it's better than a 3 or a 1, so we'll take it. Let's try one more. What's different about this one?
It's a fraction.
Fraction, tell me more.
It has a top number and a bottom number.
Top number and a bottom number. I like it. Not a top number, but a top expression, and not a bottom number, but a bottom expression. And what do we notice when we have a bottom expression? It can't be 0. Where is it equal 0? At -2. That tells me right now that we are going to have a vertical asymptote of x equals -2. That's where it's undefined. The end behavior of this graph will be the asymptote, and we will find that by doing the following. What is the limit as x goes to positive or negative infinity of 3x over x plus 2? Do you remember how we did this work the other day? Let's see if you remember. If the bottom term was of larger degree, then what was the answer? 0. If the top term was of larger degree, then what was the answer? Positive or negative infinity. If they were the same degree, then all it is just 3x divided by x, right? Which is 3. We'll show you how we actually generated this. We did the limit as x goes to infinity of, we factored out the x on the top, we factored out the x on the bottom.
Yes.
I saw the brain retrieval happening. Memory was in action.
Yep.
This went to 0. The x is divided. I got 3 over 1, which is why if they are of the same degree, we can simply take this divided by this. So we know that's just going to go away. Everybody agreed? So I can see right away that the horizontal asymptote here is x is equal to 3. So when I'm teaching this in pre-calculus, sometimes it's frustrating because we go through this whole process. Sometimes people get confused about dividing it. Like we actually take x plus 2 and we divide it into 3x. And it's no, like when you look at this, you see a structure right away. -2 and 3, like you know right away. That easy, okay? So it works out. All right, let's consider the x and y intercepts. I have the x-intercepts and y-intercepts. I set up my little table. I plug in 0 for y, I plug in 0 for x. Let's start by plugging in 0 for x. If x is 0, I get 0 over 2. And what is 0 divided by 2? 0. So you can tell it goes through the origin. I'll set this up so you can understand how it's going to work. If we set y equal to 0, say 0 is equal to 3x over x plus 2. Is a fraction equal to 0 when it's 0 in the numerator or 0 in the denominator? 0 in the numerator. If it's in the denominator, it's undefined, right? So just look at the top. 3x equals 0, what would x be? 0. If it was, say, 0 equals x minus 4 over x plus 1, what would x be in that situation? 4, wherever the top is equal to 0, okay? Wherever the top is equal to 0 is what we choose. So, what do we know about this thing? We know it goes through the origin, and we know it has some asymptotes. That's going to give us a pretty good sketch of the graph, but we need to confirm both our intervals of increasing, decreasing, and concavity, and our points of local min, local max, and inflection. And for that, I am going to need to use my first derivative test. What rule would we use to find this first derivative test? Quotient. So f prime of x is equal to, and f double prime of x is equal to, derivative of the top, 3 times x plus 2 minus the derivative of the bottom, 1. So I get just 3x there. Divided by x plus 2 quantity squared. I have 3x plus 6 minus 3x over x plus 2 quantity squared. What do you notice? Isn't that nice? We get 6 over x plus 2 quantity squared. So I'm looking for my critical points. Is the top ever equal to 0? No, it's not. Is the bottom ever equal to 0? At a value of? -2, right? Value of -2, it would be equal to 0, right? But is -2 part of the domain? So we don't list it as a critical point, but we do consider it when we are looking for our changes of values. Okay? So I plot -2, that's where the function is undefined, and we're going to use the Mika method. Okay? And we are going to look at this and say the top is always positive, and the bottom is always, except for the one time it's equal to 0, right? But it's, everybody agrees it's never negative. So therefore, positive, positive. What does this tell me about the function? It is always close. The derivative is always above the x-axis.
Yeah.
What does it tell me about the original function? If the derivative is always positive, then the original function is always on its way up. It's always increasing. It is never decreasing. That is what we know. So increasing, it's going to be from -infinity to -2, union -2 to infinity. Please do not say from -infinity to infinity, because -2 is not part of the domain. The local max happens where it changes from positive to negative. Does it change from positive to negative? No. And it doesn't change from negative to positive. So in this situation, there is absolutely no local min, and there's no local max. Was that intentional? Did you throw that at Jacob?
Maybe.
Jacob, I'd watch yourself.
Yeah.
Yeah, keep an eye out. There's no local max or local min. We could just cross that off.
Oh gosh.
We go to the second derivative, and you have some choices here. You could use the quotient rule for the second derivative. What other rule could you use? The chain. You could say I have 6 times x plus 2 to the -2 power. If you rewrite it like that, then you have 6u to the -2, and you have x plus 2. My derivative for x plus 2 is 1. My derivative for 6u to the -2 is Excellent. So my second derivative is negative 12 over x plus 2 to the third power. The bottom is to the third power, so it is not always positive. It switches back and forth between positive and negative. We use the Mika method here. We will plot negative 2. Bree, would you give me a number to the left of negative 2?
Negative 3.
Negative 3 plus 2 is negative 1. Cubed is negative, and a negative divided by a negative is a positive. Rosa, give me a number to the right of negative 2.
Negative 1.
Okay.
Or I'll pick 0.
Thank you. All right, we pick 0, and we get a positive on the bottom, and a positive or a negative divided by a positive is a negative. So I have positive and then switches to negative. So what that tells me is I have concave up. Concave up from negative infinity to negative 2. And concave down from negative 2 to infinity. Inflection is where the second derivative changes sign. Does the second derivative change sign? Yes, at negative 2. Is negative 2 part of the domain? No. So there's no point of inflection.
Take that.
Remember, this function was always increasing. It was never decreasing.
Right. What did you not?
Braden, I'm going to choose you to be my judge. Are you ready to judge me?
Yep.
Thank you. I will make a 10 by 10 graph. I'm going to go by twosies. 1, 2, 3, 4, 5. Call that 10. So my vertical asymptote is at negative 2. My horizontal asymptote is at positive 3. It goes through the coordinate of 0, 0. And notice how I know that from negative 2 to infinity here, it is concave down, and it's always on its way up. It's always increasing. So it gives me a clear picture of the graph headed like that.
This is looking good.
Now, this one up here, obviously it's increasing, so it's going to be up in this space, and it is concave up. So I'll draw it like that. And we'll see what we get. I go into my y equals, and I will take 3x, and I will divide that 3x by the quantity x plus 2. Please tell me I did a good job. I couldn't take the disappointment of being a failure again.
Right.
Okay. Always got a guilt trip that helps you with grades. Drew Lint at you.
All right, Braden, hit me with it.
A solid 8.5.
8.5. What do you think, Haley? Do you think he was too kind?
Go back to the other one. I didn't know it.
Ooh.
No, I think you actually
Yeah,
did really
that's pretty
good on
good.
that one. It looks pretty good.
Oh, I'm
The
trying.
real question is, what would Ty say?
What would Ty say?
I agree. That one's better.
That was better. Okay. Really didn't like my first work. Y'all agree. I'll look at this and this, leaves me wanting. Yeah, never as good as your
You're
best. It's
somewhere
never
in
as bad as your somewhere in between. Learn to live in the middle for crying out loud.
Right?
Yeah.
Right.
Yeah.
Normalized.
Yeah, I did. I'm just coming off a break. So it's kind of like
Same.
somebody entering a game
Are we
that's been
all?
on the bench for a while. It's like they just expect you to come out and perform. I mean, I need to warm up. I mean, who knows where I'll be fifth hour?
Right?
Probably here.
Might be not in Rosa's car because it's locked and she doesn't have the keys.
Oh my God, it's stressing me out.
All right, let's turn to your assignment. Show me what to do, what not to do.
Okay.
I just want my pager.
If you look at your very final part of your assignment that talked about the horizontal asymptotes, don't worry about that from Friday. Okay, so those last 4 problems. You just negate that. But if you flip over to the curve sketching, you're gonna see that you have a cubic for number 1, you have a quartic for number 2.
You got me with that.
As you flip it over, you have then another cubic for number 3 and a quintic for number 4. Number 5 is a rational function. 5 is what you could get through today. And I want to be clear that for this assignment, we're not going to be doing problem number 8. And I don't know about number 7. Tomorrow we're going to do one problem, and then you're going to have some time to work. So it'd be very good for you to get some of these started and worked on. You don't want to walk into class tomorrow saying, I have no idea how to do these, okay? I mean, if that's the case, come see me tomorrow morning or possibly after school today. Okay? That's where you guys are.
Hi, buddy.
We should be ready to test on Friday.